In 1995, a magnitude 6.9 earthquake struck Kobe, Japan. The physical devastation was immediate, leveling entire neighborhoods and causing the violent collapse of the Hanshin Expressway. But the physical damage was only the beginning. The power grid failed, plunging millions of people, hospitals, and critical infrastructure into sudden darkness. Traditional recovery is agonizingly slow. Rebuilding a destroyed high-voltage substation requires clearing vast tracts of land, pouring permanent concrete foundations, and executing complex on-site assembly. This process routinely takes months or even years. In a post-disaster crisis, time is the ultimate enemy. A reliance on static, slow-to-build concrete infrastructure is a dangerous flaw in our ability to respond to a grid collapse. Engineers developed a solution in the form of the Type A mobile substation. These units are high-tech first responders designed to deploy immediately when the grid fails. These units arrive fully assembled on road-legal 40-foot trailers. Because they are pre-built and tested off-site, they restore local power in a matter of days. Take this utility emergency in Ireland. A faulty circuit breaker, a device that automatically stops electricity flow during a surge, threatened a massive localized outage. The utility deployed a mobile bay, leveled the trailer on site, and interfaced directly with the existing lines to keep the power flowing. Mobile units enable high-speed logistical rescue in places where grid recovery previously required multi-year construction projects. But fitting a sprawling high-voltage power station onto a standard transport trailer is a massive physical challenge. How do engineers shrink a facility that handles 123,000 volts into such a small space? Traditional substations use open air to insulate live components. Because air isn't a perfect insulator, these parts need massive physical distance between them to prevent deadly electrical arcing. This spacing is why substations are typically so large. The breakthrough making mobility possible is Gas-Insulated Switchgear, or GIS. It combines switches and circuit breakers to protect equipment. GIS uses a specialized insulating gas instead of air to prevent arcing. This allows high-voltage components to be packed tightly together in a sealed environment. This 3D arrangement shows the result: an entire 5-bay electrical substation squeezed into the exact dimensions of a standard 40-foot shipping container. To survive highway transport, these systems are armored with pre-terminated cables and rotating air bushings that fold down for travel. They even include self-testing sensors, so they arrive on site fully sealed and verified. GIS technology doesn't just reduce the footprint, it turns sensitive electrical grids into armored plug-and-play modules capable of surviving a 1,000-mile journey. This build off-site philosophy is now being pushed to its absolute physical limit to conquer impossible geography. In the North Sea, engineers face a massive logistical hurdle: building grid infrastructure for offshore wind farms in some of the most treacherous waters on the planet. Traditional on-site construction in the ocean is a nightmare. Violent weather causes constant delays, and the environment is incredibly dangerous for engineering crews trying to assemble complex systems on a platform. The solution is the Type C semi-stationary substation. It is a colossal marine-grade evolution of the mobile trailer, built entirely on the same modular philosophy. Engineering principles born from emergency mobility provide the necessary bridge to our most remote and extreme renewable energy frontiers. The process begins safely on land, where an entire multi-thousand-ton Type C substation is built, fitted, and fully commissioned. Once verified, this building-sized pre-commissioned platform is loaded onto a specialized sea barge for its final journey. By avoiding offshore assembly, engineers remove the risks of marine construction and guarantee that every component will function the moment it is connected. The unit is dropped seamlessly into the ocean, instantly ready to link the offshore wind farm to the mainland power grid. This connectivity links high-speed emergency trailers on our highways to these colossal floating behemoths in the deep sea. Mobile substations provide a grid resilience that moves past unmovable concrete, relying instead on agile, heavily armored engineering that adapts to wherever power is needed most.